let's get started then for today's meeting.
Good morning, everybody. So today we are going to be starting the Lab 2, which is basically on debugging deep neural networks. And this recitation is going to be conducted by me and Thomas. And okay, so let's get started. I think there's an issue with the screen. Sure, yeah. Yeah, so let me just restart again. So yeah, good morning, everybody. So today we're going to be getting started with Lab 2, which is basically about debugging deep neural networks. And this is going to be basically giving you a lot of tips about debugging in your homework part 1s and part 2s. And today the lab will basically be conducted by me, Praneeth, and Thomas. So let's get started. So yeah, in computer science, debugging is something that's always big and something that we always do, which is pretty painful. In deep learning, it's a much bigger thing and it's much more painful because there are a lot of things like implementation bugs, dataset constructions, model fits, parameter choosing. And because of this, we see a lot of things that fail silently. And we thus need like really good ways to debug things. So the goal of this lab today is going to be a way to like learn some skills in debugging and kind of make it easy for you guys to actually work on your homeworks and debug some stuff. So yeah, we're going to go through how to debug our homework part 1s and how to debug our homework part 2s. And you guys will also be learning more about some of these parameter stuff and all in the part 2 homeworks. So let's get started with how to debug our homework part 1s. So actually, this is something that I used while I was doing the course as well. And this is the IPython debugger. And this is basically an interactive Python terminal debugger. And it can be used to be run in our Jupyter cells directly. And it makes it very easy to debug our code. So I'll walk you through this in some time. But yeah, basic idea is that we can actually set breakpoints in our code. And how this helps mainly is it kind of opens up an interactive Python shell wherever we put these breakpoints. We can get to know about the different variables present at that point of time, run any code at runtime itself, see if we have any issues in the code, check these variables, and then just continue. And you can go through the documentation over here through this link for IPyDB. And yeah, so these are some of the useful commands that you can actually go through while doing IPyDB. And some of the few that I find useful quite a lot are step, next, continue, and where. And so if we talk about the step command, we're actually talking about the step into command. So what this basically says is that at any point, if we're on a particular line, we can actually execute that current function at that particular line, and we can go into that function and start executing line by line. So this kind of helps us monitor every single line in that particular method that we go into. And then we also have a next function, which basically says that at any point of time, if we're on that particular line of code, it executes that function in the background, but then it immediately goes to the next line. So this is kind of like the step over, if any of you have used a Python debugger before. And then we have the continue, which basically fast forwards time and kind of gets you out of the terminal saying that we have done our debugging and we want to continue with running our cells. And we also have the where function, and the where function is kind of just going to give you a stack trace. So it kind of tells you which particular method called this in the first place. I can't hear. Okay. Is it audible for all of you guys in Zoom? Yeah, okay. So some of the useful commands we have are basically the step, next, continue, and where. The step is basically the step into function, so it helps us execute a particular function on that particular line of code, and it goes into that particular function and executes things line by line. Other than that, we have the next function, which is the step over, which executes that particular function in the background, and it immediately goes to the next line of code. So it's kind of like just a checker that that particular function works well, and then it goes to the next line. Whereas we have the continue, which basically just gets us back to the fast forward way and makes us run our notebook the normal way. And then we also have the where function, And the where function basically kind of gives us the stack trace that we're running and tells us what function is being called here, what line of code is actually leading to this particular line, and it just makes debugging much easier. And this was actually a link that I used at one time. And it's kind of like the cheat sheet, which basically gives you all the different IPDB commands that are very useful. And I'd encourage all of you to go through this after the lab once, just in case you want to get some different techniques of, debugging. Okay. So now I'm going to just talk about some of the debugging that we do in our part 1 code. So I'm sure by now all of you have gone through your part 1 homeworks, and you would have seen that a lot of matrix operations will be happening over there. And for example, we might be going through a few matrix operations such as addition. And if we see addition, let's say in the forward, it'll just be like a z equal to x plus y, where these are matrices of size m cross n. In the backward, we'll basically be considering the gradient of the loss function with respect to these particular variables. And if we calculate them, we'll be getting them in the form of like dou L by dou x equal to dou L by dou z, dou L by dou y equal to dou L by dou z and stuff. And this is for like basic addition. And then if you see the dot in a big circle around it, this is actually called in-place multiplication, where we consider let's say two matrices of size m cross n. We multiply the I comma j value at each matrix with the I comma j at the other matrix. So it's kind of an in-place multiplication that we do. And if you see the backward propagation here, we'll actually see that the dou L by dou x is equal to dou L by dou z into the in-place multiplication of the y matrix. And this is actually something that we can just do directly via the chain rule that we do in differentiation. But if you want to know more about how we can actually understand the shapes and dimensions of these things, there are a few tips we can actually keep in mind. So one very important tip is that if we have a matrix such as x or y of any size m cross n, then if we take the gradient of the loss with respect to that particular matrix, or any gradient with respect to that matrix variable, it will also have the exact same shape. So if x has shape m cross n, then dou L by dou x will always have shape m cross n, which kind of makes it easy for us to actually understand. So this has shape m cross n, this has shape m cross n, and this will also have shape m cross n. Similarly, if we were to consider the matrix operations such as matrix multiplication, where we do, let's say, the direct multiplication. So here z will be of size m cross n, x will be of size m cross k, and y will be of size k cross n. Now, once again, when we're doing the back prop, you can actually notice that we're doing dou L by dou x equal to dou L by dou z into y transpose, and dou L by dou y equal to x transpose into dou L by dz. While this might seem a little bit confusing, a few hacks that we can actually use is, as I suggested before, we can actually just see the dimension analysis via this technique. So we know that x has size m cross k, which means dou L by dou x also has size m cross k, and dou L by dou z has size m cross n, which means that the value that comes here needs to be having a size of n cross k, and that is the transpose of y. So similar to that, you can actually do the same thing here. And these are just a few techniques that if at any point of time you want to debug your back prop, see why your matrix multiplications might work better, these are just some simple tips you could use. And yeah, basically, these are the tips that you need. Okay. So I hope you guys are clear so far with everything. And okay, let's get started with the notebook right now. We'll just go through like a notebook. So if I'm hoping all of you guys have the notebook right now, and if you don't, you can go to Piazza Post 154 and download the notebook from there. And we can just kind of start going through it. I think, are you able to download the notebook?
No.
Okay. Give us 1 second. Okay. We just pasted the notebook on the chat. Can you guys see if you're able to download this? Okay. Yeah, they're able to download it from the chat.
I'm sure that he does.
Okay. Yeah, so we will update it on the post as well. But yeah, for now, you can download it from the chat. Okay. So let's get started by going through the notebook ones. So yeah. So we're going to be talking about how to debug our homework ones and homework twos, part twos over here. So yeah, let's start running these cells one by one. I'm using Collab right now to run the notebook, but yeah, I'm just going to be installing the IPDB debugger over here. Okay, cool. So I'm pretty sure all of you have gone through your homework one, part one by now. And I think most of our part ones will be following this similar structure. So you'll be seeing the handout, and inside the handout, you'll see the model, which is the basic actual model implementation that we'll be creating, which is like our CNNs, RNNs, the multi-layer perceptrons and stuff. And then we have our MyTorch library where we have all our neural network related functionalities over here. And we have our optimizer related functionalities. And you would have also noticed that we have an autograder.py and autograder flags. So this local autograder is basically the way you test your code when you're running it locally. And this is something very similar to what even your auto lab will be running in the backend to actually see whether your code is working or not. So a good way to always check your code running is use your autograder. And you can actually use these autograder flags and keep toggling them, basically set them either true or false. And based on the values, you can test your code locally at different points. And if at any point you see some small errors like no module name, MyTorch and all, just make sure you're in the right directory and make sure the local tests are being executed correctly. So yeah, if you open the autograder flags, you'll basically see flags like this. And based on the flags you see, you can basically toggle them and test different parts of your your code. Okay, cool. So now let's see a few basic tests that you can actually see and some things you need to consider while running or writing your code. So if you notice that we'll be doing a lot of matrix operations, a lot of gradient, and a lot of backprop and stuff like this. And because of this, we might lose precision of some of our numbers. And sometimes that is why we need to consider that there is some tolerance factor while seeing our numbers. And something over here that we need to consider actually is a tolerance number. So you can see that at certain points of time, only certain amounts of tolerances in the precision is allowed. So based on that, you'll have to make changes to your code and things like this. And a good way to check this is by using the NumPy all close functionality. And you can actually see what is the tolerance of the particular thing you're checking. And based on that, make your changes to your code and things like this. Similar to this, you will also have an architectural test. And basically, this is checking whether your particular matrix or your particular output dimensions are the correct sizes and things like this. And we kind of just assert shape sizes. So at any point, you just look at your NumPy array and you can just check the shape of it and make sure that the dimensions of it are the correct shape. And this is a good way to check whether everything is working well. Okay. So now we will be going through, let's consider a scenario where we have a bug in our linear layer. So if you guys see this linear layer, let me just run this. Yeah. So I don't know. On first glance, do you guys see anything wrong with this code? Like the linear layer, if you see the forward and backward functions. Let's start with the forward. Do you guys see anything wrong with the code? Cool. Yeah, in case any of you can't or like want to see, like you can actually see that over here, like we should be doing a matrix multiplication, but we're doing an in-place multiplication. So this might on first glance kind of look tough to like notice in the eye. But yeah, that's why these debuggers and stuff like this are actually useful. So let me just show you, like if we were to run this cell over here, we're basically just asserting whether everything is correct and whether it's in the right tolerance and things. And we're seeing that our forward pass test is failing basically because our forward linear right now is actually having this bug. So let us try to change it once and see if it's working correct. Yeah, so you can see that that was a fix over here and we're able to do it. But just to give you an idea on how to use the debugger or make it a little bit useful, what we can do is actually in this forward layer, we can actually, call this debugger by calling the ipdb.setTrace. So what this does over here is, now when we're executing this particular cell block, we're going to be going through the code and we're going to hit the linear.forward method over here. And then once this goes inside that, this will actually hit the setTrace function being called here and immediately opens an interactive terminal. And now you can see that we're in this particular line of code. And let's say if I press next, I go to the immediate next line of code within that function. But the advantage mainly of doing this is, now even though we're in this cell, we can actually use this as a Python shell itself, and we can run any Python commands we want. So I can kind of just do a diagnosis of what's happening. I can check maybe the shape of the cell. So now I know that the shape of Z is 2, 2. Or another way to check is maybe I just want to do the operation itself. I want to check over here itself, what is it giving me right now? It's giving me this. And let's say I'm expecting something else. I can literally just, at runtime itself, see what I want. So I know that these are the values I want. So this is just a quicker way of debugging, and you don't have to keep changing things in your cell, and you're kind of just working with things at runtime and messing around with stuff. So it's a much cleaner way and easier way to debug, and it is something that I use quite a lot. So yeah, this is an example usage of how to use the debugger in the first place. And if you're ever done with it, you can just press C, you continue, and you completely leave this, and you get out of the debugger in the first place. So it's simple, and that's kind of the use case. So yeah, let's continue though. Let's see what other errors you guys can spot. Like, do you guys see any issues with the backward in the linear? Okay, let's go with all the forwards first. Let's see in the ReLU class, do you guys see any issue with the forward function over here?
There's a question in the chat.
Is the medium one?
Hello, sorry, can you repeat? Yeah, correct. So I can see okay, let me just answer the question first. Okay, so yeah, if you don't know where the code is failing, okay, so the question is, what if you don't know which area of the code is failing, how to know where to add the debugger? So yeah, that is mainly, sometimes it's kind of like intuition. You kind of know that these could be areas that are cases of failure. Those are sometimes you add the thing. And sometimes you kind of see that the cell itself can go into fail mode. Like, let's say you don't notice the failure immediately. So basically, when we're doing this set trace, we're basically trying to see if some value that we assert is failing or not failing. And we kind of just add the ipdb.setTrace to kind of go back and see what values are causing it to fail. But sometimes we can see like a cell of the notebook itself fail. And for such cases, there's actually something called the %debug. So what the %debug does at this point of time is it kind of just does like a rewind, and it kind of just tells you where something had failed. And also, I've also mentioned one more part where you can actually use the where function of these IPDB things. And what the where does is it actually gives you the entire stack trace of what is executing what. So we can basically see our entire stack trace. And based on this also, we can kind of get an idea on what could fail. So these are just some ways in which you can kind of intuit what could be an area of failure and where you could put your breakpoint and test for different values. I hope that answered the question. Okay. And yeah, as I saw someone in the chat also put, yeah, in the ReLU function, I think self.a should not be np.minimum and it should be np.maximum, which is correct. And yeah, let us execute this cell. One second, let me also change the forward here. Yeah. So we can see now that all of these have passed. Similarly, can you guys spot the errors in the backward functions in linear? Let's start with linear. Yeah, I think basically it is matrix multiplication at both these ends. And similarly, can you guys spot the error in the ReLU? Does anyone in the class want to talk about the error that you guys can see in the ReLU backward? Okay, cool. So what we can see actually in the ReLU backward is we calculate the value of dou L by dou A, but what we're actually doing here is we're setting self.a to 1 wherever the value is 0. And we're setting it to 0 wherever the value is not 0. But instead, if you know how the ReLU activation works, it's kind of a straight line until it's kind of 0 until it's when it's negative, and then it's a straight line max from those points onwards, right? So what we have to do is if self.a is greater than 0, we set 1, or else we set 0. So this would be the change that we actually make to ReLU. So if we were to check these two changes as well, let me just here. Yeah. So you can actually see the backward tests as well passed over here. So yeah, this is just a glimpse of how to use the IPDB debugger in general. And in case any of you are using VS Code, I can just show you a small, easy snippet of how to use. I don't think my screen is sharing. But yeah, 1 second. Yeah. So just to give you an example of how to use the VS Code, you can actually set a breakpoint manually even in VS Code by doing this, by just using this toggle type point. And if you go and run your code with the debugger, okay, 1 sec, let me. This here. So let me put my breakpoint and let's say we run and debug. What we can actually see is we kind of get a list of all the function variables, local variables, and stuff like this. And we actually even have options to, 1 second. Yeah, so we can see over here, we actually have options to go into these particular things. So this is a step over, this is a step into. So if I go to step into, I go into the main function and I go one by one executing the lines. So if I go to calculate score, say for example, I can see the different variables. I see the local variable over here, which is being passed on. And I can also see all the things inside this. So this is kind of how you use these breakpoints and all. And these are just some techniques you can use for your homework 1 and homework 2. And yeah, so let's just go over everything we discussed. So work through your shapes manually before coding. Try to understand the expected dimensions of your inputs, weights, what you want, and things like this. and use as many print statements as you can, because like debugging is always more useful when you're just printing out your shapes and stuff like this wherever there's a mismatch. And yeah, go through the write-up. The write-up most of the time contains all of the information required, and it'll save a lot of your debugging time. And yeah, you can actually make use of the VS Code debugger. And I'd encourage all of you to go to the registration lectures if you haven't yet. And this has a lot of information there. So yeah, that's all from me. And now Thomas will take over and give you some information on how to debug the homework part 2s.
Okay. Good morning, everyone. Can everyone on Zoom hear me? Good, good, good. Now I'll walk you through how you can debug the part 2s for all homeworks. So the part 2 homeworks contain 4 major sections. So we always have a data loading and pre-processing section. Then we will build our model, check if our neural networks are mapped properly, and then we will train and monitor them to see if they can cross the high cutoff. So I'll give you some tips that can help you pass the early cutoff and also the high cutoff as well. Okay, so we are going to do a lot of work on the notebook. So has everyone managed to set it up on their local machine? Do you have the notebook and the data.zip file? If you haven't, there's a link in the chat. You can download that real quick. It's a small file. I'll give you a minute. In the meantime, I can walk you through some simple steps. So yeah, let's start by installing our dependencies and importing them. And the first thing you should pay attention to when you're working on your P2 homeworks is to check the device you're running your notebook on. Here I'm running on the CPU, which is fine for this simple example, but if you're training a large neural network on CPU, it won't be efficient. So make sure you have access to a GPU. So that is the first thing you should look out for. And then the next step should be understanding why we need a config for our P2. So let's say when we shared the notebook with you guys, we gave you very descriptive variable names for all the hyperparameters. So let's say when we're experimenting with our ablations, if we're not following the same pattern and we're just hard coding values, it's going to be really hard to understand and follow, especially for your study group members, because it's going to be hard to understand what 35 is doing exactly here. So as much as possible, try to store your hyperparameter values in configs. It makes it readable and easier to maintain as well. So you don't have to remember where you switch the config. You can just switch the config in a centralized place. In addition, the config is also sent to 1DB. So let's say if your study group members are running different ablations, you can see which hyperparameters they're using. So it's going to be really easy to replicate their work. Okay. And you can also add additional hyperparameters. So let's say if you're working with different schedulers and optimizers, you can add those values here. So try to track as much as possible inside this config dictionary. Makes it really easy to debug and understand how your neural network is wired. Okay. Did all of you manage to download the data.zip file and set up the notebook? Can you give me a thumbs up if you have? Okay, cool. So for this simple example, you should just see 2 MFCC files and 2 transcripts. this is just a toy example, so we're not going to load much. And then let's plot our MFCC and see what is going on here. So this is basically a representation of our audio file. So the x-axis tells us the time steps. So each is going to be like a few milliseconds of your, it represents a few milliseconds of your audio file, and the features will capture the details. So let's see, some of the features are capturing the loudness, others are maybe capturing the tone or pronunciation. It could be, they could capture different things. So the more features we have, the more details we can capture. And this MFCC is the standard way we work with speech recognition systems. So this is a standard input. But before we proceed, I have a quick question. Now, in its current format, we have a single MFCC file. Can we use that to train our neural network? Or do we need to do some pre-processing? You can unmute from Zoom or drop it on the text, on the chat. Or if anyone from the classroom wants to chip in. What do we need to do to this MFCC file to make it ready for training?
Can you hear me?
Yes.
Yeah, so I think from what I see, you basically have the transcript file, as string values, and if you need to train, then you need to be able to convert those to integers.
Yes. Yeah, that's
Or
a good
floats.
point. That's a good point. And in addition, if you pay attention here, you can see that it's not normalized. So some of the features have values that can reach 150 decibels, some are minus 50. So when you're training your neural network, it's going to be hard to set an appropriate learning rate so that it can train across all the features. So we need to normalize it. And in addition, we also need to give it some context so that the neural network can predict the appropriate phoneme. So that's what we're going to do.
I have a question.
Sure.
Can you go back to the image?
Sure.
Okay, so there is a gap in between, right?
Yeah.
Why is that gap that is happening in between? Yeah, in the image, there is a gap, yeah, there. Yeah.
Yeah, so here we haven't applied any type of time or frequency mapping. So this is just a coincidence. If you can zoom and pay attention, you can see that there are some values here. It's not completely zero. So we haven't applied any type of masking here. So it's just a coincidence. Does that answer your question? Okay.
Can I ask a very basic question?
On the chat?
Hello, can you hear me?
Yeah.
Oh, basically for each task we make a file and put everything inside, like, or is everything downloadable? Like on the left of your screen, I see there's a Lab2 file, file folder, and under that there's data, and then there's IPYNB. So is the data also provided, and is everything, so every time we should make a folder like this?
Yes, the data is provided and the folder structure doesn't matter. So here you can set it. So I'm telling it to point to my data folder. So this depends on how you set up and structure your files. So you can find the data.zip on Zoom. Maybe Pranit, you can point at the data. Yeah, so this doesn't matter. On your homeworks, it might have a different folder structure. So you just have to.
Yes, thank you. Is the file folder also provided, or we have to download it somewhere?
Yeah, so Pranit will point you to where you can get that.
Oh, Lab2.
Come again?
I mean, where do we get the data?
It's on the Zoom chat. You can download it from the Zoom chat. There's a link.
Okay, thank you. And can I check if I understand it correctly? So basically, if we use IDE like VS Code, it is better because there's debugging mode. So it's better than the Colab from the very beginning for this two tasks, part one task, because it's it's not computing power like highly required. So
Yes.
IDE is better choice, right?
Yes, you're correct. So for the P1s, it's easier to work with VS Code. But for P2s, you also have to train. So it's better if you work on Colab or Cargo or someplace you can get access to GPU. Or you can also work with PSC if you prefer VS Code. You can set it up with, you can set up VS Code with PSC. I'll point you to a recitation video on how to do that later.
Thank you so much.
Okay. Okay. Yeah, so we have to pre-process this data in order to make it ready for training. So that is what we're going to do inside our audio datasets. So we're going to load the MCC file, normalize it, then we'll concatenate them all into one. Then we apply padding because we are going to have a sliding context window. So we need to apply padding at the top and bottom. And then after that, after applying the context, we have to break it into frames. So for each time step, we will apply the context from top and bottom and break it into frames. Then if we want, we can apply time and frequency masking, which can help it generalize well and pass the high cutoff. Yeah, but this is basically what we're going to do inside the audio dataset. So one of the most common issues you'll encounter is when you're normalizing, you have to pay attention to which axis you're using. So sometimes it's not always 0, it can also be 1. So for instance, in this case, we're trying to normalize across the row. So we have to use axis 0. But depending on your data, you might need to normalize across the column as well. So you have to pay attention to the axis you're using. So this, yeah, you pay attention when normalizing. Then apply the padding appropriately. So depending on the library you're using, the syntax is different. If you're using Torch, PyTorch, pay attention to the syntax you're using. So it's a bit different on PyTorch compared to NumPy. So apply the padding. And as Praneet mentioned, try to print the shape after each operation. It's going to help you debug. So we can actually go through this. So in this example, our individual MFCC file, the shape is 10 by 27. So let's say what happens if I concatenate it. So we only have 2 MFCC files, right? So if I concatenate it, it's going to be 20 by 27. And then if I apply padding, let's see the context I'm using. So if I'm using 10, it means I'm going to apply 10 at the top and bottom. So this is going to be 40 because we have applied 10 at the top and bottom. And then for each time step or for each MCCFF file, we're going to split it into frames. But if you get the point, it will help you debug. So you can see the shape and it's easier to spot where things have gone wrong. If something, if you've done the calculations wrong or if there's a bug in your code, printing the shapes will help you debug. Okay, and at the end of each section, there's a checkpoint. So try to answer as many as possible. And at the end of the lab, you can tell us how far you are able to follow on Piazza. So we also need to do the same processing for our transcripts. So for our transcripts, we similarly have to load them. We remove the start of sequence and end of sequence symbols. We concatenate them all into one. Then we need to do mapping. So yeah, someone earlier mentioned why we need to do mapping. So we can't give characters we can't feed it into our neural network. We have to give it numbers. So that's what we are doing here. We are trying to map each phenome into its respective index. So we convert all the transcripts into a numerical format. Then we group them into batches. So that's what happens for our transcripts. So at this point, we are more or less ready for training. So you can see the output and experiment here. So if you've managed to follow so far, you can just experiment and see what happens. Let's say if I don't apply normalization, what happens to my MFCC file? You can see that the value, the range is big, the gap is big. You can see that it ranges from 0 to 80, but if you apply it, you can see that the mean value across the row is 1 and the standard deviation is 0. So you can use the same learning rate to train your model across all the features. You can also experiment with the context. So right now I've added a context value of 4, so you can see that it has been padded at the start, but let's see what happens if I remove it. Yeah. So play around with it to make sure that you understand what is going on here. Yeah, and try to answer the checkpoints as well. So what makes our train and validation dataset different from our test dataset? The answer is right here, but does someone want to try? What makes it different? So what's the difference between the train validation dataset and the test dataset? True, yes, we don't have the transcripts. True. Something else you've noticed? We don't apply masking as well. So we only apply time and frequency mapping during training so that it can generalize well. So what we're doing when we are applying time and frequency mapping is we're just removing a few of the rows and columns. So that changes the data set and helps it generalize well. So you can't always have a perfect data set during inference. So let's say my mic can go out for a millisecond or 2, so there might be a gap in that audio file. So that's what you're trying to replicate, trying to make your model as robust as possible. So let's see how batch size comes into play. So if you're using a large batch size, let's say for your homework, you're using 1024 or 512, you're going to have a smooth gradient because the weight updates are done less frequently compared to, let's say, a batch size of 4. So if my batch size is small, the training is going to be noisy, and it's also going to take longer compared to a bigger batch size. But the trade-off is if your batch size is big, all of them might not be able to fit into your RAM. So let's say if you're using Kaggle especially, you have to pay attention to your batch size because if you use a big number, it might not be able to fit into your memory, so your training might fail. So pay attention to the batch size, especially when working with low resource setting. Okay, and you can experiment with time and frequency masking, but we're not going to cover it during this lab. And now we have managed to process our data pre-process our data. The next step is to build our model. So the most common issue here is sometimes we might forget to make sure that what flows out of one layer can fit into the next one. So whatever the output here has to match the input here. So if these two are not matching, then you won't be able to proceed. It's going to throw an error. So let's try it out real quick. Yep, it's going to throw an error. So you have to make sure that your output from one layer matches the input to the next. Cool. And here you can see the total parameters. So for your P1, make sure that this is less than 20 million. So yeah, the more parameters you have, the more powerful your model is going to be. So yeah, it's nice to have a lot of parameters if you have the compute power, but for this homework, 20 million is the limit. Now we have managed to pre-process our data. We have configured our network. Now, at this point, you should be able to cross the early cutoff. So the next step is to pass the high cutoff. So you're going to divide ablations with your study group members, and you're going to try a lot of experiments. And now we're going to see which experiments are worth keeping and which ones we should stop early, so that we can get to experiment with a lot of with different type of architectures. So yeah, let's start with the first one. So here you can see our training accuracy and our validation accuracy, the training loss and validation loss as well, and the learning rate. So do you think we should keep this going, or should we stop it early? Does someone want to try? Yeah, it's not learning at all. So accuracy is not improving, the validation, both of them are not improving, and the training loss is not improving as well. So we have to stop it early. And what about the second one? So if you can see the validation score right here, the validation accuracy, it's not converging at all. So we're having a very noisy training, so it suggests maybe our learning rate is a bit high, or it might be stuck in a local optima. So we should experiment with the learning rate and train again. So I would stop this early as well. Okay, let's go to the third one. What do you guys think about the third one? Let me see the questions also. Okay, I see a couple of keep it. Yeah, the chart looks good. You can see that it's converging, our validation and training accuracy. They're both converging, but if you pay attention to the value, the accuracy is really low. So 30% accuracy is not good enough for your P1, for your P2. So you should definitely stop this. Maybe try increasing the number of parameters because your model is not performing well. So the chart looks good, but the accuracy is not good enough. So we have to stop this as well.
Thomas, I have a question for number 2.
Okay.
So we see how the loss for validation is decreasing, but the accuracy isn't changing. Does that mean, like for some data points, the model is fitting really well, but on average, like it's not really fitting well for most of the other data points?
Yeah, so especially for training, it's a bit stable, but for validation, that's what's happening. I found this a bit strange as well. So maybe they did the color grading wrong. So this should have been the validation loss because this one is smoother compared to, oh, sorry, I got this wrong. No, actually, the blue line, you can see that it's more noisy, but on this side, it's a bit smoother. So the color grading might have been wrong. I think that's what created the confusion.
Oh, okay.
Yeah. Okay, so let's move to number 4. What do you guys think about number 4? The accuracy looks good enough. It's around 88. The validation is around 86. Yeah, this one is a bit tricky, but I would stop it right around here because if you pay attention, the validation accuracy is not increasing at all, but the training accuracy is increasing, which suggests that it might be overfitting. So stopping somewhere around here would be ideal before it overfits to the training data. So yeah, always pay attention to the validation accuracy to make sure that it's at least learning something. Okay, and number 5. Here we don't have the training accuracy. Training and validation accuracy is just training loss and validation loss. What do you guys think about this? So the validation loss is increasing, but our training loss looks good. Should we keep it? Yep, this is overfitting. So we should definitely stop this. And let's see number 6. So training accuracy is increasing slightly, especially towards the end. And validation accuracy is following as well. Same thing is happening on the side. Yeah, I see, keep it. Yeah, I think this looks good enough. So we should definitely keep it. Yeah, so there's no science to it. It's just an intuition. So yeah, you just have to tell when it's going really bad so that you can stop it early so that you don't waste your time and your compute. So yeah, if you see something like this, this is good. You should keep it going. Yeah, and let us know what you guys think here. Yeah. And finally, hopefully at this point, you have managed to cross the high cutoff and it's time to submit. This is the easy part. So you only have to pay attention to one thing. Just make sure that the size of your test data set is equal to the number of rows in your CSV file. So as long as this is correct, then you're good to go. Just make sure you use the whole test data set to test your model. Yeah, thank you, everyone. This is the end of Lab 2. If you have questions, you can drop it on the Piazza discussion, and you can let us know how far you've managed to follow. If you
Hello.
have any, yeah.
I had a question. When you talked about the batch size and saving space on like RAM and we're using Colab, the question was, does changing the batch size also have an effect on the model performance, like apart from just saving on compute?
Yeah, so if I got your question right, you're asking if the data set is going to affect our model performance?
The batch size specifically.
Oh, yes, it will. So all the hyperparameters you configure will affect your model performance. So you can get good results with even a smaller batch size, but you just have to be aware of the trade-off. So when you're using a small batch size, training is going to take longer, and the gradient is going to be a bit noisy. So if possible, try to use a larger batch size, but sometimes you may not have enough compute. So you should just be aware of the trade-off.
And what does that mean? Like the gradient being noisy?
Let me show you one. So you can see here that it's a bit noisy because it's shooting up and down, oscillating. Because the batch size is small, we're going to have a lot of updates. So it's going to make it a bit noisy.
Thank you.
Another question. For this experiment, basically we're only trying to modify the parameters like batch size, like the times we train, right?
Yeah.
And one other very basic question. So when we set this up, when we try to run this code from the very beginning, we have to import a lot of packages. And I think at the very beginning, we have been taught to use Anaconda. So I'm not sure if I just import those packages, they will be in the environment of Conda environment.
Yes. So if you're using the Conda environment created for the homeworks, most of these libraries should be there. You just have to install 2 libraries for this lab. So
okay, thank you.
That's a good point. You should always activate your Conda environment. I forgot to do it, but yeah, it's always good to use Conda environment.
How to do that? Can you walk me through?
Sure. So if you're using VS Code, you can always come here and select a kernel. So select Python environments, and you can see all the Conda environments you have, and select the Conda environment for the homeworks, which is IDL Spring 26. Or you can do it on the terminal. So yeah, but this is not relevant if you're using notebooks. So yeah, disregard this. But you can always use Conda, activate, and then the name of the environment. But if you're running notebooks, just do it here. Does that answer your question?
I'm using PyCharm instead of VS Code. Not sure if it's a better choice. If it is a good choice.
I guess it's subjective. I've never tried PyCharm before, but if that is what you prefer, I think you should be fine.
Okay, I'm trying.
Okay.
Thank you.
Okay. Any other questions?
Oh, yeah, I've got one. So when we are like modifying parameters and the net and the architecture itself, would you recommend us to like do the training with just, I don't know, 20% of the data set, or to try it with the whole data set?
Especially when you're experimenting early on, you should use a subset, especially when you're trying to cross the early cutoff, because you're going to run into a lot of errors, so you don't want to use the whole data. It just makes the whole process slower. So in order to pass the early cutoff, just use a subset, maybe 10%. Even 5 is okay. But
okay,
if you want to cross the high cutoff,
yeah,
use
that one. So use the whole data set if I'm working on the high cutoff.
Yes.
Okay, thank you. And also, like I saw that we could also use like convolutional, like not only linear layers, but also be able to use like conv 2D. Would you recommend it, or should we just stick with linear layers and batch norm?
Yeah, so you're not allowed to use convolutional networks
Okay.
on this homework.
Okay, so only linear layers.
Yeah.
Got it. Thank you.
Okay. All right, everyone.
Sorry,
Okay.
a quick one. Is there like a Piazza post on how to submit homework 1? I don't know, it's a bit confusing and I don't think there's enough instruction on the write-up. So I'm not sure like what we're supposed to, homework 1, part 1, sorry, that's what I meant.
If I'm not mistaken, there's a whole section about submission on the write-up. If you have found that and you're still struggling, please make a Piazza post and I'll try to help you.
There's no section on oh sorry. Never mind. Yeah, I've seen it. Thank you.
Okay. Any other questions? All right, everyone.
I could go and post the chat if you want for homework 1P1 as the submission.
Yeah, so sorry, I didn't catch your name, but Pranit has put a link for you if you're still struggling to submit for homework 1P1.
Thank you.
Okay. Great. Yeah, I think that's it for Lab 2. Do you have anything to add, Pranit? Okay. All right, guys. Have a good day and good luck with your P1.